Hello everybody, so welcome back for part 12 of this video series. I'm getting ready for a summer camp teaching teenagers game development. I have a week-long camp, 3 hours a day. So I was giving the lectures I have planned a trial run, and I've already come up with a couple changes, like uh, starting off with interesting meshes ate up a whole bunch of time. That'll burn up the whole first day. So probably need to do simple stuff the first day, and then add the meshes on like the second or third day. More interesting meshes on the second or third day. That way we can get stuff going quick. But still, I thought I'd share the videos that I was using to evaluate my plan on YouTube because other people might be interested in it. And so far, we got this little landscape and our character brought in. So we're ready to start doing stuff with our logic. We hit run the scene to get a quick test. Um, we can see so far our character moves with the default arrows. And jump up and down. That's just some default movement that Godot has on characters. But there's no light, so we can't really see anything yet. So light is going to be our next one. And our character's scripting is going to be a little bit complex. It's going to get a little bit complex fairly quickly. So light is an important part of games. That's something we want to have a lot of control over. So I was also thinking that would make a good example of simple movement, and we'll just kind of set it up like the sun and move it around the sky to add a touch of realism to the game. So it's like starts at the low horizon, and then over I don't know, an hour or so, it rotates across the sky like the sun, changing shadows and stuff. And that will make a nice introduction to some simple movement and a simple script because our player script is going to get fairly complicated. So might not want to jump in that just yet. Uh, ease into the scripting. But before we get into that, we've seen before, if I select the player, go over to the player here. One of our most important things is going to be our transform data. That's our position, sometimes labeled as location in other game engines, and rotation and scale. Those don't usually get other names, but uh, where are where is the object at? How is it oriented? And how big or small is it stretched out to? That's the main control and data we will use to keep track of what's going on in things. And you'll notice that there's a lot of pieces to it. So transform is actually a tensor. It's a vector where each component is a vector. And before we get into controlling, doing stuff with that, we need at least a quick preview of what a vector is. So let's talk about that real quick, and then we'll come back and script it up. So once we know what we're dealing with. So we're going to talk about vectors here. So what's a good definition for it? Avoiding the technical math definitions, we could think of this as essentially a collection of numbers um, connected into a single multi-part value. So that uh, sounds kind of fancy, and this is a little bit very simplified from the technical math definition, which if you're very serious about game development, you're eventually going to want to take some linear algebra courses and learn about all those technical things in detail so that you know what to do because it's also important for computers in general, but we can kind of bypass and simplify it because of simplifications worked into our programming languages. So a collection of numbers that are connected into a single part value. So the first one we obviously think of that is going to show up a lot in game development as well is going to be our location. I'm just going to use the pen instead of typing this in. And I'm going to notate vectors as a matrix, in particular as a column matrix. So we'll put things going down. So we have XYZ coordinates. So at some spot in space. So we're maybe like 3 units over, 4 units, uh, 3 units in one direction, 4 units over. So maybe forward to the right and 2 units up. And that gives us a location in space. But that's not the only place we use vectors. Color would be a vector. where again, it's a three-dimensional vector. Each one of our numbers here relates to a single dimension. And with color, we have, in color space, we have red, green, and blue. So location space, that when you probably think of first, the horizontal and vertical axes, which for the game engine we're using here, so in the game engine we're in, the Y is the vertical direction. So this would actually be um, 3 units to the right, 2 units forward, and 4 units up from the origin. And sorry about that little delay there. I realized I should probably turn the highlighter on the pen so it shows up better on the video. And then color space is also a vector. We have red, green, and blue dimensions making up color space. So if we had maybe, I don't know, 148 in the red, 160 in the green, and 34 in the blue, those dimensions, those numbers go together to give us a yellow color. Or, I don't know, a 35, 180, 42, just a little bit of red, a whole lot of green, and a little bit of blue would make a dark green, almost a forest green. I'm going to go ahead and put that label on there. So almost a forest green color. And I included those labels because eventually, if you're getting into game dev, you're going to want to have some idea of how those colors mix. You're probably more aware of color mixing in the magenta, yellow, and cyan, which you would have learned as red, yellow, and blue because we learned that in like first grade before we learned words like magenta and cyan. Uh, that's how reflected light mixes. But since we're in game dev, we're doing things on a screen, so we're using source light, so we need the red, green, and blue mixture. But those dimensions go together. It's a collection of numbers that go into a single multi-part value. And I have one more example here, which is sort of the generic example that um, is often used for math, like real world math, not math class math, because part of what's so confusing about this is the math class thing. But the standard example for how we would use math in the real world would be like budgeting at the grocery store, right? Budgeting at the grocery store. So that's our typical example, but is that a single number? Usually not, because we take more values into consideration. So for the grocery store, um, obviously there's the cost. That's what's usually used in this example, but that's not the only thing we take into consideration. Because if you went into the grocery store with only cost in mind, you could head over to the section with the really good cheese and burn through your whole budget and not even have a day's worth of food. So there's usually two things involved, right? How much are we spending and how much are we getting for that cost? So our typical example, the way we as humans normally think about numbers involve multiple parts. So vectors do come naturally to us. Try not to get confused with the pure mathematical class. I often like to make the separation between math class and usable math. And working with more than one number at a time is something that actually comes natural to humans. We just don't realize it because it gets so complicated and the way we do it and notate it in math class that we lose track of that. So remember that you are used to working with more than one direction at a time. It's just when we notate it, it seems very different than what comes instinctually from us. And that's a quick view of what vectors are. It's just the multiple numbers go together. So think of the generic example, budgeting a grocery. We have the cost and the quantity. We don't consider just one or the other. We don't think about only how much we're spending. because then we might not have enough food for the week or whatever it is. Nor do we think about only the amount of food we're getting, because then we could very quickly pass our budget. So those values go together, or those individual numbers go together into the value we're actually concerned about. And how do we think about these? That's the other thing to look at. So you're probably familiar with points in space. I hope you're familiar with points in space, at least that for the minimum, right? We have, I'll do it in 2 dimensions, but it's just a natural extension up to the third dimension. So we have our XY axis, like axes like we normally see in space. Uh, so a 2-dimensional vector with an X component and a Y component. And we kind of split that up by each one of our units. So a couple units over, a couple units up, and maybe we go 3 units over and 4 units up, and then that locates a spot in space. Our individual points, and we would call that 3, 4. And it's 3, 4 with this x, y vector as the basis. That's going to be an important word coming up here in just a second. Well, actually, I'll go ahead and talk about the basis first. So we have this x dimension and this y dimension, and those go together to mark out all of our spots. But that's not a restriction. We could use anything. We could use this 3, 4, 5 triangle that I kind of drew here as a basis. So maybe we have a vertical direction. I'll call it V. And instead of measuring from the horizontal, we're in a situation where it's more useful to measure from the vertical. From a diagonal. So then we have our U and V basis. It's no longer at right angles. Our coordinates were, but we could still mark out a grid here based off that. It's not a square grid, but that might be more useful for a situation. So we're not restricted to those right angles like you saw in math class. Or we could make our basis 2 entirely different things. Maybe it's useful to have, well, let me try to draw a straighter line there. Maybe it's useful to have this going off at this angle and then going off at this angle. Once again, we have two things. I'll call it M and N just to make up some numbers or some labels. So we have this MN basis that we could mark any single point. From whatever our origin is, we came down this angle and then over at this angle to find that point in space. Just like we do with the right angles, it's a little bit easier to keep track of these. But our basis is something we need to keep track of. That'll be important when we get over there and do stuff. So we're used to the XY or the XYZ basis since our game's actually going to be in 3 dimensions. That's just an easy extension from that. And we have the points in there, but that's not necessarily the best way to think about it when we think about things moving. Because if we want to get from this point over to like a point over here, we need to think about every part separately. So there's a better way to think about that. And that's where our approach to vectors in games comes in. And the biggest difference, I'll scroll down a little and go back to that original XY basis. So maybe we're still concerned about that same spot, the 3 units over and 4 units up, but with a vector instead of a point. When we think about 3 units over and 4 units up, instead of thinking about just that individual point in space, what we'd really want to think about is the arrow that goes from the origin to that spot in space. So instead of thinking about that spot in space as an individual independent thing, think about the arrow of how do we get to that spot in space. And that's the approach we want to have for vectors. Um, and then when we need to start doing math with it, at least to start off and before it gets too complicated, and change colors here, a good way to think about this is if we think about these components separately. We have our X and our Y components separately, then that gives us a right triangle. And most of us see the Pythagorean theorem way back in elementary school. If we change these labels, so we have our X dimension and our Y dimension equals maybe that, I'll write length, an L, equals the length of that arrow squared. So the Pythagorean theorem, like we learned way back in elementary school with some different labels, should be enough to get us started. You might need to get up to trigonometry and worry about that angle in the distance. There's different things, but mostly thinking about the triangle. And if you've never encountered it, the Pythagorean theorem does scale up to any number of dimensions. So if instead of the two-dimensional plane, we have the X, Y, Z, three-dimensional thing, and then some random vector coming out here to a point in space, the Pythagorean theorem still, it scales up naturally. So our X dimension squared plus our Y dimension squared plus our Z dimension squared will give us that result. Oh, that's a good letter to use for it. The result of that, which would be the length of that arrow that starts at the origin and comes to the point we're worried about. And then we can get into basis, because just like there's nothing locking this in space, there's nothing really locking our starting point in space. So then we think about it frame by frame in the game. So maybe that's the first frame of the game. And now we have a new starting point. So in the next one, the next frame of the game, we're only concerned about, from that starting point, the movement to that position we want to get to. And then we have a new starting point again, a new basis to start off. We'll have some different location and rotation and possibly scale, so all of our transform data changes at every frame in the game. And then what we're really concerned about is that movement between them. So instead of thinking of the individual point in space, for vectors, we want to think about how do we get from our starting point to that location in space. So the arrow that goes there instead of just the point at the tip of the arrow. And then every frame of the game, we have a new starting point, a new basis to work off of. And our basis is our transform. So not just the location, but we have a new rotation and a new scale factor at every spot, at every new starting point. And that's how we want to think about these numbers, but we still work with them individually. So we need to do a little bit of vector math. So this looks like it's already coming on 20 minutes, so getting long. So I'll do that in the next video, a really short one, just to show them scalar multiplication and addition and subtraction of vectors. We shouldn't have to do a whole lot of vector multiplication in game development, but we will do scalar multiplication and addition, and I'll do that in the next video because this one's already up to 20 minutes. So I'll see you in the next video.